So, we just pick up another method and a topic which relates to texturing, but solvent texturing. So, till now what we have been talking about was thermal means. We did mention in the case of cellulosic spun yarns that it is possible to use solvents also, but solvents can be used for any fiber which responds to the solvents. So, it has been used for various purposes, but we will discuss how this can also be utilized for texturing. So, in the last lecture we learned that twist texturing of spun yarns can be accomplished by chemical cross-linking, which means you have a cross-linking agent and then you do some chemical reactions under a certain temperature and time conditions, which also means you have a specific type of cross-linking agents which are bifunctional, and you need some catalysis so that the reaction can take place at a reasonable temperature so that the degradation of the fiber does not take place. And a concept of high temperature curing, that means which is close to the setting temperatures of synthetic fibers, one can go, which also means that you go to higher temperature, reduce the time, and if you use this type of a method of curing, then you can do texturing of blends as well. And if time becomes shorter, then continuous texturing in a false twist machine is also possible. So, texturing by solvents is what we will work on. Theoretically, this should be similar to what we do as a thermomechanical texturing. So, the process in general would be similar process. So, you do twist, set, retwist. This is the process people have used. Generally, people have used in a batch process that you actually make a twisted yarn, take a lee and then do the solvent process and then retwist after the process is over. That can be done, and this kind of a thing can be done only in multifilament yarn. If you have a spun yarn, then you can use the other process, which is slightly modified process, which is the ply twisting, set and retwist. As we mentioned last time, do if there are two yarns which have been ply twisted, then you can go past the neutral ply twist and then do, but the setting will be different here, and the setting can be through the solvent process. So, this also can be considered as thermo-chemo-mechanical texturing, because you are using a solvent which is a chemical. You may use a temperature higher than, let us say, room temperature to rapidize the process, and mechanical because we are twisting, detwisting. So, all that is there. So, this is also in the same category of texturing processes. So, setting, which is the key component, is by release of energy. That is why we can say that this is just like thermomechanical texturing, which believes in release of energy, as against what we discussed in the previous lecture was that we use cross-linking agent, which is not setting by release of energy. So, this is going back to the same thing. So, solvent, the word solvent always means it will dissolve something, right, but we are not interested in dissolving the fiber. It is something like we are not interested in melting the fiber in a thermomechanical texturing. So, in some sense this term solvent is a misnomer. So, it is not dissolving the fiber. Actually, this term has come because almost various organic compounds are called solvents. So, they are solvent for something or the other, not necessarily for the fiber which we want to texturize. But what will you do? Because in the earlier case we were interested in partial melting and recrystallization, Here also we are interested in partial decrystallization followed by recrystallization, because if we do not do this decrystallization, the molecular chains may not be able to do justice to the setting. That is, release of energy means what? Either they will disorient or they will crystallize. So, those processes are common, and so this will happen only when you do some decrystallization. So, these type of materials, the solvents which we call, are going to do decrystallization, and we will be interested in recrystallization. Like you said, heating and then cooling. So, that also will be there. Solvent uptake and solvent removal. A final product will not have a solvent, but solvent will be required during the process. So, if these solvents are not the real solvents which dissolve, then what are they? They could be considered as a plasticizers, effect as a plasticizing effect. That means the distance between the chains is being increased because of the presence of some such molecules. So, whatever intermolecular forces were there, they will be broken down, because the solvent molecules will enter, diffuse and things. This is how anything dissolves. So, they are also going to break intermolecular forces. They will also allow relaxation and then stabilization of a new structure. So, all those three things which were being done in the thermomechanical texturing, they also will be valid here as well. Only thing is, there you are using kinetic energy to separate the molecules. Here, in some sense, some kinetic energy may be there, because every molecule at a given temperature vibrates. So, all those vibrations become 0 only at absolute 0. Otherwise, there are vibrations of various kinds, but it is facilitated if a solvent molecule is available. So, it will again go between the molecules, break the crystallites, and obviously partial, because we do not want to lose the fiber itself. So, this is the similarity that we have discussed with the thermal setting. Okay. So, partial melting, recrystallization, relaxation of molecules to the best energetically favorable configuration. So, you do heating, cooling, here you have solvent uptake and solvent removal. So, this type of a crystallization can be considered as a solvent induced crystallization. That crystallization was thermally induced crystallization. Then you have a stress induced crystallization, like you do drawing, then the crystallization will take place. Now, this is solvent induced crystallization. The crystallization is a thermodynamic process, will take place, but you are facilitating the same relaxation of molecules by adding solvent to this polymer system. So, like we were talking about going to the lowest energy state. So, when we mix two systems here, like a delta G of mixing, we are mixing two, let us say two solvents are there, you want to mix them. So, they will mix spontaneously or not spontaneously, will also be dependent on this. So, when these kind of things happens, that energy that we are talking about can be also related to enthalpy of the system, and it can be a determining factor as well, because delta S is always going to be positive, and therefore, the magnitude of this so called enthalpy will decide whether delta G is going to be negative or not. So, when you mix certain things, you know that you mix sodium hydroxide in water, there is heat which comes out. You put ammonium chloride in water, it becomes cold. So, mixing itself, because there is energy involved, something, a molecule goes into the solution. So, whether it likes to go into solution or does not like to go into solution, based on that the delta H of mixing is going to be determined. So, in some sense, whether your solvent which you are going to use is going to interact with the polymer or not. Like you take acetone and try to interact with polyester, you may find there is hardly any interaction. You can keep washing, nothing. But if you take metacresol, things can be different. Therefore, and that means they are going to interact, and that would depend on whether they like it or not. Delta S increase everything likes in the world. So, dissolution is going to be facilitated as far as delta S is concerned. So, that means if someone can measure what is the heat of mixing, then maybe you can get an idea whether the solvent is going to really work better, work not so nicely, right. So, there is this solution theory proposed by Hildebrand and Scattered, which talks about that how can you calculate the heat of mixing. So, heat of mixing, let us say there are two solvents or a solute and a solvent, then it is related to this term which is the total volume of mixing, also is related with a term called cohesive energy density. If it is a more crystalline material, then it will be difficult, the delta E to separate them is going to be more, and the small v, which is the molar volume of that material, let us say a solvent is got a molar volume, it has got some molar volume. So, it is related to the cohesive energy, that means whether the molecules are in the crystalline form or they are amorphous already. So, if an amorphous system, maybe you will require less energy to separate them out, and so there is one, let us say solvent, the other is solute. So, what it says is that the cohesive energy density of these two things are related with a square root of cohesive energy density and a difference of the square root of the cohesive energy density, and if you square them up and multiplied by volume fraction. So, how much is the solvent, how much solute, or how much is one solvent versus the other solvent. So, this is how these people proposed a theory based on which one can estimate the enthalpy of mixing, because in the previous case, let us say enthalpy becomes 0, then it is always negative. So, this term in some sense also is telling that if this cohesive energy density of the two are close or are equal, equal will be always difficult because there are two different molecules, so it cannot be same. So, if it is solvent, then it is like energy of vaporization, like activation energy. If it is a solid thing, then maybe activation in terms of the crystallite, how the crystals will separate out, right. And so, this is what they proposed, and incidentally they also said that this particular term, that the square root of this was called the solubility parameter. Whether a polymer will dissolve in a solvent or not may not be governed only by a solubility parameter, but it is a good indicator considering the previous equation. If the solubility parameters of the two systems are similar, quite near each other, then it may be possible that dissolution may be spontaneous, right. Although we are not interested in dissolving, but it is a mixing system. So, you can always call some interaction. So, for a spontaneous dissolution, we may be requiring that delta 1 minus delta 2 is as close to 0 as possible, right. If it is there, then delta Hm will be 0 and the interaction will take place better. Now, you extrapolate this hypothesis for polymer solvent, solute versus solvent, solvent versus solvent is a very different situation, than polymer. Polymer is a long molecule, and if you look at our polymer like textile, then you have a semi-crystalline material. So, diffusion in the amorphous region can take place easily, relatively. It will take more time to get into that. And so, polymer, this thing may not be directly applicable, but still if solubility parameters of solvents and solubility parameters of the polymers are available, then you can make a right guess, some guess. Let us try these rather than try everything else. But there are assumptions. When you take polymer and a solvent, and we use even this Hildebrand-Scatcherd equation, so the assumptions. One of the assumptions is that it is going to be quite difficult for somebody to say what is the center of a molecule of a polymer. They say, well, there may be some segments which may be moving, like for example, we say segmental mobility. So, it is not the whole polymer molecule is vibrating, but if sub-segments which are free are vibrating. So, this is one assumption, that if this kind of a thing happens, you are not discussing the whole polymer, then it will be more complex. You also say that the potential energy, this is interesting, obviously, like potential energy of the polymer segment in the solvent continuum. So, there is a whole over solvent and there is this polymer potential energy of the polymer segment, and the reverse of it, that is the solvent in the polymer continuum. There is a lot of polymer amorphous region solvent is going there. So, whether it is inside solvent is inside the polymer, polymer is inside the solvent, this potential is approximately same. Otherwise, what will happen is the solvent would not go inside, because there is, like, let us say the potential energy increases, then why the solvent will go in. So, this is an assumption that the molecular volume of the polymer segment and that of the solvent are not too different. So, that segment which is moving. So, it will be quite difficult to ensure this, that the interaction forces between the two. After all, interaction means, if suppose it was a van der Waals forces being formed, it is a polar bonds are being formed and they are the ones which are to be broken. So, there is an interaction. So, one molecule going and replacing the other part of a thing. So, the forces which exist between the solvent molecule and the polymer segment part, it is assumed that these forces will be acting at some center of the molecule. There is a molecule or a segment which is a center, there is a mass, and there is a mass and there is a center of that molecule of a solvent. They act at the center to center, otherwise some of the things may be difficult. And this is interesting, that there is no volume change in a mixing. It is like when you add sugar to water, the sugar, a good amount of sugar just dissolves, but you do not really see change in the total volume. So, this is also part of an assumption, which may be true, may not be true. So, if this is what there and the mixing is random, like, so you are doing agitation or whatever you are doing, said it is not that only one part is dissolving first, then the next part goes. No. So, anywhere, wherever solvent can go, the resolution interaction will start. There is kind of assumptions. So, within that and the parameters that we have, some conclusions could be drawn. So, this is true that all these are not going to be valid in a practical situation, and therefore, the results which you obtain by the equation may differ from the actual measurements that you may do. Also, this particular theory postulates that either the reactions of the dissolution or mixing process is either endothermic or is athermic. If it is 0, then athermic. If it is some positive, then endothermic process. But there is a possibility that you can have an exothermic mixing also, which this equation does not talk about, which would mean, because it takes a square. So, this value is always 0 or a positive, but if negative thing is there, it cannot obviously explain this part of it. But it also is a fact that majority of polymer solvent interactions are actually endothermic. So, to some extent you may be able to get results which are all right. So, we just discussed some of the experiments people did. So, one interesting results which people talked about was that polyester has a solubility parameter of about 10.7. So, Ribnik and co-workers did an extensive work on trying to find out which solvent is going to work and which solvent not going to, based on solubility parameter itself. Polyester was a very interesting case to begin with, and what they found was that if you have lot of solvents, they took lot of solvents. So, some were having solubility parameter here, but a large number of were here also, some were here, some were here, but there was a thing, and some may have been here as well, right, some solvents. And what they observed was that majority of the solvents which were considered as nice solvents, they appeared in some bands which are, if you just draw a curve like this, I mean normally you would expect wherever this matches, it should be the maximum interaction. But they found that there are interactions which happen nicely are actually those solvents lie in two bands. And the typical case here was, so this is the value 10.7. The typical case was acetone. Acetone is very close to 10.7, but acetone does not affect polyester. So, in some sense there was some speculation as to what has happened. So, theory is completely failed. But they found that no, that on both sides there is some range, let us say between 9 to 10 and between 11 to 11.5 to 13, this band, these solvents were very active. And so, after a bit of a study, they could understand that polyester has two segments. One is aliphatic segment, which is the because of glycol, other is the aromatic segment because of phthalic acid. So, these segments vibrate and interact in different ways, and so polyester by itself on an average may have some value, but the segments have different way to interact because they are different as a chemistry part. Because when somebody says that only the segment of a molecule is going to work, so which segment is actually interacting? So, it has got two different segments which are interesting segments. So, they found that solvents which are lying on this left side are more interacting with the aromatic segment. Solvent on this side interact with the aliphatic segment. So, there is complexity in trying to explain. It is very easy when you have simple molecules of solute and a solvent or two solvents mixing can be very easily explained and may be able to get good results. When you talk about polymers, it may not really happen in that way, but at least it still is near. So, the solvents which are very far off are not good obviously, but exactly in the center also they are not, one or two solvents were not really working because they were either happy with the aliphatic part of the polyester nor the aromatic part of the polyester, and therefore, it is segmental stuff. And what they had measured was solubility and decrease in the initial modulus of the material. So, fiber is there. So, if solvent is dying plasticizing, it is entering. So, the modulus it will become pliable material. So, you measure the modulus. So, you do a stress strain curve and then take the modulus at every point at different solvents, obviously treated at a certain fixed time, and then you plot this curve. So, it is a complex experiment, and at the end you draw some conclusions, but it is a very interesting observation which was considered by these workers. So, what do you stand is that the solubility parameter does give some indication that the solvent is going to be more interactive or not, and such performance, such experiments can be performed on various fibers that somebody is interested in, and then think of going for texturizing. One more study was done which was not measuring the solubility parameter, but directly measuring the effect of solvent. So, there are two things which happen with a solvent is it can either help in crystallization. So, you measure how much crystallization is taking place, a long process. So, you do some treatment, then go and measure the crystalline development, then say, well, this is acting more, or reverse of it. So, our material, which is called the textile, it shrinks when you heat, and it also shrinks when you put in a solvent. So, if you take a fiber, what a length, and then put it in some solvent which interacts, you suddenly find the fiber shrinks, right. So, and that is dependent on the interaction that happens. So, some studies on shrinkage of the fiber filament which takes place in a certain solvent could also be a quick indicator whether it is going to work or not work. So, some studies which were called the isothermal studies, that you have a fixed temperature at which you are observing the shrinkage of fiber with time. Nothing is instantaneous. So, it is not that just you put there inside the thing and suddenly everything will shrink, it will take time. And why would it take time? Because initially solvent must diffuse inside, only then changes in molecular orientation will take place. So, invariably some curves which you draw with respect to time may be like this, and after some time you may find there is an equilibrium shrinkage which has been obtained at a given temperature. Okay. If you change the temperature, the curve will be different. So, it is an isothermal study. That is why we said it can be a thermo-chemo-mechanical texturing, because the same solvent you work at a higher temperature, if you can, then maybe systems can work faster. So, the rate of shrinkage can change within the same solvent as you change the temperature, or you have a solvent A and you have a solvent B which may work like this, may work like this. So, some can go like this. So, very less time here. So, it is like a sigmoidal curve. So, this shows if this is longer means the rate, the induction time is more. So, first diffusion takes place and then it will say. So, when you say I want to put it for a certain time where the setting should take place, this type of an equilibrium must be achieved. So, you can say, well, this can go to up this time, or this can go up to this time. This can be, you can accomplish your processes earlier. So, it is like the same kind of things you do. So, same solvent, different solvents at different temperatures can give you this thing, and so you will have an idea. It is a quicker solvent, so I can work on this. It takes, C for example, takes a lot of time, and also shrinkage is not very high, which also means that the intermolecular changes in orientation or crystallization may not be so fast or may not be so much without solubility parameter. Then another shrinkage test was done where it is not isothermal, but you are increasing the temperature. So, you have a fiber which is hanging in a solvent at a certain weight, you are measuring shrinkage. So, start from a lower temperature. So, you find that, well, the shrinkage is not very high to begin with. At a certain temperature, suddenly shrinkage starts. After a certain temperature, the curve becomes slow, which means for that temperature equilibrium shrinkage is approximately coming. So, here this temperature is rising, okay, like you have a DSC, you see a rate of heating, you can set up the rate of heating. Similarly, you can have a cell where the fiber is hanging and the temperature of the solvent in the cell is increasing, let us say, at a constant rate, all right. So, time is also part of this whole game, right. So, rate of increase of temperature is there. So, you get a curve like this till at a temperature it becomes almost, it just breaks because totally getting into the dissolution part of it. So, you can get this curve. From this curve, they could relate one interesting thing, that is, if you extrapolate this part of the curve and go to some point which we call a T0, temperature for 0 shrinkage. So, it is not absolute 0, it is some temperature where in this solvent there will be no shrinkage, to find that out, right. So, if you go there, no shrinkage. So, obviously, you will not work there, but what they correlated, that this temperature which is T0 could be correlated with the glass transition temperature of the polymer solvent system. Like you said, when you have a nylon, in a dry state Tg is 60, 65, you put in water, the Tg becomes below room temperature. That means the glass transition temperature is dependent on the interaction that take place. On the case of polyester and water, Tg is unchanged. So, in some sense this is also indicating that polymer solvent are going to interact, right. So, if this T0 becomes higher or T0 is lower, if T0 is minus thing, then you are quite sure at room temperature also you can do texturing. If the T0 is coming to, let us say, 40 degrees, so definitely you can't do anything below 40 degrees, you have to go above 40 degrees to do certain things. Therefore, we say that it is a combination of time and temperature and a solvent polymer together. So, this particular curve is a very useful curve, think of it, no, it is a very useful curve. You just put a filament in a solvent where you can change the thing, draw this curve, and then you suddenly get another parameter which is quite indicative whether it is going to be interacting higher, less, and where and what temperature you should use to get effective, let us say, texturing, which means decrystallization, recrystallization, everything else. So, some people did solvent texturing. How? As I said, take the filament, do the twisting, take the Lee, put it in a solvent for a certain period of time, remove the solvent either by drying or by a non-solvent, and then untwist, and you get beautiful effects. But obviously, the time required here is not 0.1 second or 0.2 second, the time required could be in minutes or seconds, but this time, as we know, can be changed if you increase the temperature. For example, polyester with two solvents, one is called methylene chloride. This solvent has a boiling point which is low, right. So, you can't go at a temperature which is higher than the boiling point. So, you will be working at a lower temperature. Rate of setting would be lower. Interacting, it is not that it is not interacting, interactive, but at low. So, all experiments will have to be done at low. TCE, which is trichloroethylene, its boiling point is high, it also interacts. So, you can actually say, well, we will do this setting maybe at 80 degrees. So, if you do at 80 degrees, times can reduce. So, you can come from minutes to seconds. So, that is what is there. So, people have worked with methylene chloride on polyester, people have worked with tetrachloroethane, all right. Nylon formic acid, dissolves nylons, right. But so, you do not use formic acid, but you use solutions of formic acid in water. So, if you reduce the concentration, it will not dissolve. The same solvent, if you reduce the concentration, will act like a plasticizer, and so you will optimize what concentration. So, acetate with acetone or also methylene chloride in a different concentration have been used. Acetate, for example, we said it cannot be texturized by thermomechanical means because the tensile strength goes down rapidly when the temperature and crystallization occurs. So, in such cases you have a solvent assisted texturing. You can go to higher temperatures, whatever the, let us say the solvent can go, or just below that, and the temperature will be much lower for doing this compared to if there was no solvent. So, such material, like we say acrylic fiber cannot be melt spun, so you do solution spinning. So, if you say acetate fiber cannot be thermomechanically textured, but you can do solvent assisted thermomechanical, then can be done without degradation. Time is different story. So, people obviously have worked on the blends also in a solvent itself, but if there is a blend, so how do we work around? One solvent for one part of the fiber and the other solvent for the other part of the fiber may be different, like polyester, viscose, there are different kind of solvents, and there is a blend. How do you work? So, one work has done that if you use a solvent where a cross-linking agent can be dissolved and conditions are created in such a manner that cross-link takes place in the wet state, called a wet cross-linking, not a dry cross-linking like in the last lecture we discussed. So, in a wet state, some of the agents can make covalent cross-link. So, let us say epoxide, one of the example is epichlorohydrin, it can make cross-link in a wet state. And what solvent? Diisocyanate also we said can, diisocyanate does not like water, right, but it can be dissolved in organic solvents. So, if there is an organic solvent which interacts, let us say on one part of the blend, let us say polyester, epichlorohydrin in that solvent if done correctly will do the cross linking. So, you can have a simultaneously cross linking going on and the synthetic part of the fiber acting as a because of the solvent polymer interaction, and in one go you may be able to texturize. So, texturing of polyester viscose blends have been attempted like this as well. So, we stop here. So, solvent texturing of synthetic yarns and their blends can be done. So, solvent induced crystallization takes place. Here we can just mention, if somebody asks a question, does the crystallization take place during solvent uptake or solvent removal? Whether the crystallization will take place during solvent uptake or solvent removal. Removal is not necessary. It is exactly whether the crystallization takes place during heating or during cooling. Main thing is when the solvent is there, molecule can move around, right. So, they will go to a new configuration when it is possible to go. If you completely remove, then they cannot obviously, but yes, again you will get a curve like you have the rate of crystallization curve in a solvent also, which will mean during solvent uptake decrystallization will take place and recrystallization can also take place. And of course, finally, when you remove the solvent, then it is freezing in position, like you are solidifying, you are stabilizing structures. Now, motions will not take place so much because solvent has been removed from the molecules. So, solubility parameter which we went through can also give some idea, and the Hildebrand's scattered theory of mixing talks about the enthalpy measurement, and shrinkage in a solvent can help to find a suitable solvent for texturing. And we also understood why wet cross linking may be needed, right. If you are already wet, cross linking also could be done in a solvent. There we are. Thank you.